Right, so today we're just going to have a little look at a really useful thing which you can do in MATLAB, which is solve ordinary differential equations. So there's lots of ways you can solve them and lots of things you can do with them, but we're just going to have a look at the simplest example, which might be the most powerful way, using ODE45 and functions. So here we have a quick program where we just clear all the variables, and we're going to be numerically integrating this equation, which is like exponential growth, but for a population which has a carrying capacity k. So in this, the rate of growth of the population, which is the number of the population divided by, which is dn by dt, is equal to some rate of growth r, which in this case is 1, multiplied by the population. And if this term didn't exist, then this would just be exponential growth. But here we have it's slowing. When n approaches k, then this bracketed term approaches 0. When n is much smaller than k, then it's approximately unity, but when n approaches k, this goes to 0. And when n is greater than k, this is negative. So we have a negative rate of growth when n is above the carrying capacity. So this is like in some, for instance, a bacterial population, when there is some certain amount of food in the environment, and a population of k is the carrying capacity, and the populations will tend to that. So here are these variables which we're going to use in this differential equation. Now here we have the actual, we have a function which includes the differential equation. Now this has to be set up in quite a particular way to be used with ODE45. So we have it saved in the same folder here. This is just an example folder, and we have to pass it this variable time. It doesn't have to be t, but it's used in the function, and we have to pass it the initial positions at each step, and we get these output conditions. This variable here is a structure, a data structure in MATLAB, and this is how we can pass in variables. So we're just using it here to pass in the values r and k. So we're setting them here, var.r equals r and var.k equals k, and then we're extracting them over here, because the global variables don't cross into the different functions. So here we've got a very simple equation, just the equation we've written here, where out is the first derivative and in is the number of values, the values n. And we've just written the equation out here, and it's very, as you see, it's very simple. Now, if we go back to this equation, we then have these initial conditions n, which we have in a variable called start, and this is the end time. So in ODE45, which is the function which is going to do the integration, we use this at, and then the growth equation, which is just the name of our equation, which is in the same folder. This area is the time that we're integrating from, so starting at 0 and ending at time t end, which we've got as 20. Start here is just a variable which has the initial conditions, and in this case we're starting with a population of 1. Options gives this ODE option set. The default, I think, so these tolerances, these are related to the steps between each point of the integration. In ODE45 it uses a 4th and 5th order Runge-Kutta method to calculate each point in the when it solves the ODE, and the difference between those in each step, if it's less than 1 times 10 to the minus 4 in this case, then it's fine, and if it's more than that, then it will reduce the time step and recalculate it. So it's not actually anything to do with any actual error which we'll actually encounter. It's an internal variable, so it doesn't so you can't rely on that on being some particular parameter if you need to constrain it. But we can lower these if we want to have more precise results, or sorry, that for the epsilon that would be true. And we can lower these if we want to have more precise results, or we can raise these numbers if we don't care about precision. This runs perfectly quickly, so it doesn't really matter. And here at the end, we can put in this structuring, this structure with the variables in which we're including. And here we're just plotting the values. So very quickly this program runs, and you see in this particular example we've solved the differential equation. This is a known solution. We start off at n equals 1, which we can see it does, and we finish at the expected value of k equals 1000. So this is how you can solve a first order differential equation in MATLAB. Now just to explore this example, we can see that we can do lots with it. We can make it last for a longer period of time. We could say we want to run it for 300 time units, and you can see we just have more of this plateau. We might want to decrease the carrying capacity just to see what effect that has. It should be fairly obvious that it decreases it to 500. We may want to look at what starting on different numbers gives us. So if we start at a much larger population, you see we don't have that characteristic slope up, but we still have the same form of the equation, and it does all of the things you would expect it to. So this is as you can see, a perfectly reasonable way of solving this. Now there are other useful things which we can do with the differential equation solver, which we'll cover at a later point. So this is for solving a first order equation. We'll look at in the future how to solve a second order differential equation and higher order ones. Perhaps how to look in its limited use for partial differential equations, although that might be a little bit more challenging. There are different ODE solvers. There's ODE45, which is a good initial guess at picking one. There's also ODE113, which can help with some stiffer problems. And we'll have a look at some more of the variables, and also doing it without this function ODE45, which is obviously only in MATLAB. So I hope that's helpful and gives you a basic understanding of which terms you need to have into these into the solver, and how to get it to produce a differential equation and to solve it.